Welcome to The Explainer. Today, we're diving into the invisible forces that make our world heat up and cool down. We're going to break down the basic chemistry of energy, and you'll see the science behind reactions that are happening all around you, and even inside of you, right this very second.
So have you ever actually wondered about that? You mix a couple of things together and suddenly it gets warm. You mix two other things and boom, it gets surprisingly cold. I promise you, it's not magic. It's a fundamental principle of chemistry that's at play everywhere, from a roaring campfire to one of those instant cold packs.
And we can see this happen right in a lab. Look at this. In one beaker, you dissolve some sodium hydroxide in water, and the temperature just shoots up. It gets really hot. But in the other one, you dissolve ammonium chloride in water, and the temperature drops. It gets cold. You're doing the same basic thing, but you get the exact opposite result. So what on earth is going on here? To get to the bottom of this mystery, we first have to get a handle on two key tools scientists use: temperature and heat. Now, you might think they're the same thing, but in science, they are critically different. Understanding this difference is everything. Okay, so let's dive in. Temperature. It's not actually heat. What it is a measurement. It tells you how much the tiny little atoms and molecules inside something are moving around, how much they're vibrating. You can think of it as a reading of the microscopic chaos inside an object. The faster all those little particles are zipping around, the higher the temperature. Heat, on the other hand, is all about the flow of that energy. It's energy on the move. And just like water always flows downhill, heat always moves from something with a higher temperature to something with a lower temperature. Always. It's the energy that's in transit. Okay, so with those ideas in our back pocket, we can go back to our beakers. And now we can see that we're looking at two totally opposite types of reactions. One of them is giving away energy, and the other one is taking it in. So that hot beaker, that's what we call an exothermic reaction. Exo means out, and thermic means heat, so it literally just means heat out. This reaction is dumping energy into the water around it, making the water particles move faster, and that's why the temperature goes up. A really simple way to think about it is like this. The stuff you start with, the reactants, they transform into new stuff, the products, and there's leftover energy from that change. That energy gets released as heat, and that heat is exactly what we feel as warmth. Now this is where it gets really interesting. This slide shows it perfectly. It's like a ball rolling downhill. The reactants, our starting materials, begin with a whole lot of stored chemical energy. As the reaction happens, that energy is let go, released into the world, and the final products end up in a much more stable, lower energy state. And the cold beaker? Well, that's an endothermic reaction. You guessed it, endo means in. So this reaction means heat in. To even happen at all, it has to pull energy from its surroundings. Right, so in this case, the reaction is literally fueled by the heat around it. It can't happen unless it pulls in that energy. It yanks heat away from the water, which causes the water's particles to slow way down. And that's why the beaker feels cold when you touch it. And here we see the complete opposite picture. It's like having to push that ball uphill. The reactants start out with less energy, and they have to actively absorb energy from the outside world just to get to the finish line. They end up in a higher energy state than where they started. Now, this isn't just stuff that happens in a lab with beakers. Not at all. These are fundamental processes that power our entire world, and even our own bodies. Once you know what you're looking for, you'll start to see them absolutely everywhere. Just take a look at some of these. The fire that keeps you warm? That's combustion, a classic exothermic reaction. The energy your body's using right now to listen to me? That comes from cellular respiration, another one. But then on the flip side, you have photosynthesis, this huge planet-wide endothermic process where plants soak up sunlight to create their food. And that instant cold pack for a sprained ankle? Yep, that's a handy, portable endothermic reaction right in your first aid kit. But you know, just saying hot or cold isn't really good enough for science, right? This isn't just a feeling we're talking about. It's a real physical change that you can actually measure. So how do scientists put a number on it? How do they quantify exactly how much energy is moving around?
Oh, absolutely. We definitely don't have to guess. There's a way to put a hard, precise number on that flow of energy. So how do they do it?
They use this really elegant and powerful equation. I know, it looks simple, maybe a little intimidating, but it lets us calculate the heat change with amazing precision. Let's just break down what each of those letters means.
Okay, so Q is the big one. That's the quantity of heat we're trying to find. To get it, you just need three things. M is for mass. That's easy. It's just how much stuff there is. Theta is the change in temperature. You can measure that with a thermometer, no problem. And then there's C. Now, C is the really cool one. It's called specific heat capacity. It's kind of like a substance's thermal personality. Water, for instance, has a really high C. It's stubborn. It takes a ton of energy to heat up. Sand has a low C, so it heats up super fast on the beach. Once you know those three things, you can calculate the exact energy transferred in joules.
See? Understanding the difference between giving heat and taking it, it's not just for chemists. You've basically unlocked a new way to see the world. From the food that's fueling you to the air conditioner that's cooling you, our entire existence is balanced on these constant, invisible exchanges of energy. Just look around and you'll see it everywhere. A whole world built on these simple, powerful rules of hot and cold.